Hello and welcome to Physics 262 Pre-Lecture Notes. I'm Dr. Steve Brule. In today's lesson we're going to learn how to calculate the capacitance of a network of capacitors. We'll find out why capacitors in parallel see the same voltage. We'll find out why capacitors in series must all possess the same amount of charge. We'll calculate the amount of charge and voltage on capacitors either in series or parallel. And we'll learn to reduce complex capacitor circuits to a combination of series and parallel capacitor networks. And then we'll use the rules for simple parallel and series capacitor networks to ultimately find the charge and voltage on each capacitor in a complex network. Well, let's start by drawing a diagram of two capacitors that are hooked in parallel to a battery. So, in order to hook capacitors in parallel, I'm going to draw them as if they were holding hands. So the hands that they're holding are right here. See, here's one hand. They're holding one hand here, and they're holding another hand here. So there they are, two hands holding, one hand on one side and the other hand on the other side. So if you can draw a line from one plate of the capacitor to another plate, those two plates, and draw a line on the other side to the alternate plates, then those plates are in parallel. And we could also say that those plates are parallel with the battery up here, because they're holding hands with both sides of the battery as well. Well, if you have two capacitors in parallel, they see the same voltage because they're touching using conductors, and we know that conductors are, if we're in static equilibrium, those conductors have the same potential throughout. So this is all at one potential here, and this is all at another potential on the other side. So if I grounded the negative terminal here, then that would be 0 volts here, and let's say that's a 9-volt battery, so then this would be at 9 volts on that side, and that side is also at 9 volts. Well, how can we find the total charge on this parallel combination? Since we can recover the charge, I'm going to have to remember to talk about this when we get to series, because I just remembered I didn't put this in. But since the charge, if we remove the battery and then try to recover the charge that the battery placed on, we can recover charge from both of these capacitors. So the total charge on this parallel network is just the sum of both of the charges. We're going to see that when we have capacitors in series, you can't recover all of the charge on both capacitors. So how can we find the equivalent capacitance of this parallel combination of capacitors? Well, I'm just applying Hitler's equation for capacitance, Q equals CV for Q1 and Q2. This is really, whenever you do this, it's Q1 equals C1 V1. I said 2. Q1 is equal to C1 V1. Q2 is equal to C2 V2. See, you always have to apply Hitler's law to each capacitor, and I'm going to advocate for students to always use these subscripts so you always know what capacitor and voltage and charge you're talking about, because otherwise what happens is we get these big circuits and we're using Hitler's equation over and over again, and then and what happens is students might use Q3 and use capacitance 2, 4, and potential 3 to 1. So they're using all these different capacitors and voltages and charges, mixing them all up, and that doesn't work. You always have to use the same subscript for each one, and you'll see how that works. All right, so to find the equivalent capacitance here, then we just used Hitler's equation. We're saying that the total charge on a parallel combination of capacitors is the sum of both charges. Well, there's Hitler's equation for both charges. And then I factor out C1 and C2, or I factor out this voltage because I know that V1 is equal to V2. V1 equals V2, which is equal to the overall voltage here. So I can factor that out, and then we have the equivalent capacitance is, since we know Q equals CV, so this must be Q total equals C total times V total. So this must be the total capacitance of the parallel combination of C1 and C2. So for parallel capacitors, you just add up the capacitance, and that's the capacitance of the parallel combination. Well, let's draw two capacitors in series. When we draw capacitors in series, we have to make them in such a way that if you were an ant walking along this path and you went through one of the capacitors, the only way to get out is to go through the other capacitor. So if that's the case, then those two capacitors are in series. Here's a nice analogy for you. So here are all these people waiting in line, and every person that goes through one door has to then go through the next door, and then they have to also go through that third door. So I would say that these three doors are all in series with one another. So our analogy for series is the doors that if you go through one, you have to go through another. So in this case, I've got two capacitors that are in series. If I go through one of them, I have to go through the other one. So this is a door, and I have to go through both the doors to get out. But if they were in parallel, I would, like if we go back to the parallel combination, I can go through this one and get back to the battery without going through the other one. So they're not in series. We know they're in parallel because they are holding hands. Okay, so we've got holding hands and going through the doors, and that's how we know whether an element is in series or parallel. So why must the charge on each capacitor in series always be the same? Now this is one of those things that I'm showing you why it is, and I'm expecting all of you students to remember this. Well, we're just, and here's the little derivation I'm going to go through. First of all, I just grounded this end because I like to do that so that when we have a battery, we can think of, if this is a 100-volt battery, we can say, well, this is at ground, so that's potential of 0 all along here, and then the potential all along here is going to be at 100 volts. Otherwise, if you don't have any kind of reference, you don't know where the 0 is, then you could have a 100-volt battery, and then if this reference wasn't on there, this might be at negative 50 volts, and this might be at positive 50 volts, and nobody would ever know. So that's why I always like to draw in my ground so I know what I'm talking about. Or I might have this, I could ground this side, and that potential would be 0, and then over here we'd have negative 100 volts. All right, so let's look at how the capacitors charge when they're in series. So if we're taking, and we're imagining positive charge moving over here, but what's really happening, I wish I had done this using electrons, but I didn't. So we imagine positive charge moving along the wire and then occupying this plate over here and giving it plus Q charge. Well, when that happens, that plus Q is going to attract negative charge from over here. So the electrons are going to move over here and end up being on this plate, so that we end up with minus Q on the second plate and plus Q on the first plate. So that's how capacitors always work. You always have plus Q and minus Q. You already knew that, didn't you? You better, because it was in one of the previous shows. So a way to remember this, a way to remember this is that when these internal plates that are connected together on capacitors that are in series, when the charge that this plate acquired, it had to steal it from the other plate. So it had to pull electrons away from the plate that it was attached to in order to give it negative Q here. And then since it pulled negative Q away from this plate, that means it leaves this plate charged with positive Q. So those internal plates all have to have the same Q, and then we already know that from the way that capacitors work, that that Q on the internal plates is equal to the Q on the outer plates, and well, here it is, the electrons are coming from the other side of the battery and occupying that charge. So then what happens is in series, all of the plates have the same amount of charge. They all have either plus Q or minus Q. So two capacitors in series have the same amount of charge. And it doesn't matter if this was C2 was 100 microfarads and C1 was 1 microfarad. It doesn't matter. They both have the same amount of charge. It's always got to be the same if they're in series. And this is the thing that I'd forgot to put into the show, but I'm glad I'd remembered it, is that the amount of charge, let's see if I did that. I did it in a different way. So the amount of charge that's available, so once this battery charges up these capacitors, it's giving out on this side, it gives plus Q on that side, and it gives a minus Q charge on this side. And it cannot recover the charge that's internal here. So the total charge that's stored on this capacitor network is just the charge that you have on either plate. Now there's fancy ways that you can get the charge back using switches, and we'll talk about those in class. There's people who are clever have devised ways to recover that charge that's stored on the internal plates of capacitors in series, and it's kind of a nifty way to, well, you'll see. You electrical engineers will like that. Okay, so the available charge is just the charge that's on the outer plates, the internal plates. Once you remove this battery and try to recover the charge, so you recover this charge and this charge, the charge that's on the internal plates of the series combination, that those electrons just migrate back over to the protons that they came from and neutralize one another. All right, so let's see how I did this. So for each one of these capacitors that's in series, the voltage across them, we can use Hitler's equation, Q equals CV, solve for the voltage. So we can say V1, so here's capacitor 1, V1 is equal to Q1 over C1, and V2 is Q2 over C2. And notice I didn't put in Q1 and Q2 when I made this video because they're all the same Qs. But I like to, if I'd done it again, I would put in those Q1s and Q2s, and I would write off to the side Q1 equals Q2 equals Q, because the overall charge which is available from this series network is just Q. And it's also, each one of the capacitors has that same charge on it. It's kind of a funny thing with series capacitors, isn't it? A little tricky. Okay, so then I just wrote the Hitler's equation for each one of these capacitors, V1 and V2. Well, I know that the total voltage, when I have a battery like this, the total voltage of each element has to add up to the voltage of the battery. So the sum in series, the sum of the voltages is equal to the total voltage. So I just add V1 plus V2, and that's going to give me my total voltage. And then I just put those Q1 over C1 here, Q2 over C2 here, and then I factored out the Q because it's the same charge on each capacitor in series. I hope you're getting that. Oh, I just factored it out. And then solving for Q, I just divide both sides by that quantity. And so then you end up with V divided by 1 over C1 plus 1 over C2. So this is the capacitance of a series combination of capacitors. It's 1 over C1 plus 1 over C2, and if we had C3, we'd add 1 over C3 plus dot, dot, dot. As many capacitors as we have in series, you just throw them in there. So there we have it. This is a summary of what we've just learned. The two equations, if we reduce the parallel capacitors, we just add them up to get the capacitance of this parallel combination. If we have series capacitors, we add up this funny 1 over series. Okay, well, in the rest of the video, we're just going to work some examples. Let's find out the charge on each one of these capacitors that's in this, and you should notice, is this series or parallel? It's series because if you were an ant walking through this circuit and went through this door, you'd have to also go through this door to get out. You're not allowed to turn around once you get going. All right, so how are we going to find the charge and voltage on this? The first thing we do is we find the equivalent capacitance of those two capacitors in series. So I use the equation for the equivalent series capacitance of two capacitors. And I've got a 10 and a 30, so I take 1 over 10 plus 1 over 30. I end up with 7.5 microfarads is the equivalent capacitance of those two in series. Then I apply Hitler's equation, Q12, which is the total capacitance, the total charge is equal to the total capacitance times the total voltage. Well, the total capacitance I just worked out, that's the capacitance of the two in series. The total voltage is the voltage on that series combination of capacitors. So I multiply those two together, and then I get the total charge. See how it's handy to use those subscripts every time we're talking about the voltages and so forth? Because if I had just said Q equals CV, maybe you're thinking the voltage here and the charge here, or whatever. You get mixed up. Okay, so now, and I always write this out to make sure I know what I'm doing. In a series combination of capacitors, I know that the charge has to be the same. And because this plate right here has to steal charge from that plate, and the amount of charge it steals is the same amount of charge that guy loses. So those always have to be the same, and then the charge on a capacitor, the two plates of a capacitor, is always the same. So the charge on each element is the same. So here's Q1, Q2, and they're both the same amount of charge. It's the same charge that we have across the entire element, which is the amount of charge that's available if we try to recover it. Okay, then I just apply Hitler's equation individually to find out the voltage for each one of those capacitors. So I'd already found out the charge on each one, so I found out, let's go back just a step, so that when I said that when I calculated this total charge here, that's the charge on these two plates really, but then I make the note that that's also the charge across these two plates and these two plates. So this is Q1, Q2, and each one of them is equal to 750 microcoulombs. Okay, so then I apply, for each capacitor individually, I apply Hitler's equation and solve for the voltage. So there's voltage 1 is Q1 over C1. Take 750 microcoulombs over 10 microfarads, and I can find 75 volts are across this guy. And then for the larger capacitor, we take the same amount of charge. That was the total charge on the entire circuit, but I know that it also has a charge of 750 here too. So Q2 divided by C2 gives me the voltage on C2. And those add up to 100 because we know that if we have series elements, that if we jump up 100, we go down 75, we're going to have to go down another 25 to get back to our 0 if we have that grounded. All right, here's another circuit. This is a little more complex. We've got 4 capacitors now. Do you see any elements that are in either series or parallel? Why don't you press pause and think about it for a minute. Let me ask you this. Here's something that a lot of students would say. They say C1 is in series with C2. Would you say that? Is C1 in series with C2? Press pause and think about it. Well, the answer should have been no, because if you were a little ant going through this door, you don't have to go through C2 door to get back to where you started. You could go through this door, and then you could go through that door instead of C2. Or you could go through this door instead of C2. So C2 is not in series with C1. So what you should have noticed is that these three capacitors are all holding hands. They all touch on this side, and they all touch on the other side. So they both are, all three of them are holding hands all together. So that means that those three capacitors are all in parallel. And when I replace those three capacitors from the circuit, so these, I'm going to cut the circuit just like this, and I'm going to take these three capacitors and replace it with a single equivalent capacitance, and I'm going to call it C234. 234. See how I'm using these subscripts to help understand and keep track of what I'm doing throughout the circuit. The biggest problem students have with these is that they lose track of what capacitance and what voltage that they're dealing with after they've gone through a few of these steps. So I advocate for you to always use these subscripts to keep track of what you're doing. Alright, so now we redraw the circuit with the equivalent capacitor. So instead of these three capacitors, now I've drawn just this one capacitor and call it C234. I can calculate the equivalent capacitance of this parallel combination of capacitors now by just adding up those capacitors, because in parallel we just add capacitance to find the equivalent capacitance of the combination. So there you go, and each one of the capacitors was 10 microfarads in this circuit, even C1 is. So now we've got C1 and C234. Can you tell, are they in parallel or series? Well, you should notice that if you were an ant going through this door, you would have to go through that door to get out. So those two elements are in series with one another. So I'm going to calculate the equivalent capacitance of those two capacitors in series by using my equation for the equivalent capacitance of series capacitors. So that's 1 over C1, which was 10, plus 1 over C234, which was 30. We just calculated that. And I end up with 7.5 microfarads as the equivalent capacitance of these two capacitors together. And now I'm done. Well, I'm not. I'm done going the one way. I've reduced the original circuit that we started with here that had 4 capacitors. I've reduced that to a single capacitor. And once you do that, the step is always the same. You find the total charge on the total capacitance. So to do that, we apply Hitler's equation for the total, and look how I use these subscripts. So C1234, that was the capacitance of all 4 capacitors, is equal, Q1234 is equal to C1234 times V1234. So I just calculated the total capacitance of the 4 capacitors together, and the total voltage on the circuit was 50 volts. So I find the total charge, that's Q1234, is 375 microcoulombs. Now I'm going to go backwards. So now that I have the total charge on the equivalent circuit, I'm going to go back the other way and find out the charge on each one of these elements. And every time you go backwards, you have to ask yourself the same question. Is charge the same or is voltage the same? So when you look and you're going back from this diagram to the one just previous to it, will I say that the charge on each one of these is the same, or is it the voltage is the same? Think about that for a second and come back to our show. Well, what you should have said is that since these two elements are in series, I know that the charge has to be the same. So I'm going to say the charge on C1 is equal to the charge on 234. And that's equal to the charge on 1234, because that's how it works in series. You get it? I hope so. Now, how can we find V1? Okay, so now I know that the charge on each one of those capacitors, I've utilized the fact that I know that charge in series is the same for capacitors. And now that I know the charge on each one of those, and I know the capacitance on each one, I can just apply Hitler's equation at this point and find the voltage for each one. So, Q equals CV, but I'm always going to use a subscript. So I'll say Q1 equals C1 V1, or down here I'll say Q234 equals C234 times V234. If you don't use the subscripts, you get mixed up. Okay, so then here's Hitler's equation, solving for the voltage, and we knew that the charge was the same for each one of those because they're in series. So I put Q1, which is Q total also, divided by C1, and I get 37.5 volts on V1. And then for Q234, I knew that the charge on that capacitor was this 375 also, divided by the capacitance, and I get 12.5. And it's, as a double check, the voltages in that series loop have to add up to 50 volts, and sure enough, they do. 37.5 plus 12.5 is 50. Well, we're done with C1 now because we already have the charge and voltage on that element. We have the charge and voltage on C234, but we're not interested in that. We wanted to know what the charge and voltage on each one of the capacitors in C2 and C3 and C4 were. So now we're going to have to go backwards again. So when we go backwards from here to here, are we going to say that the charge, the Q2, Q3, and Q4 are equal to Q234? Or are we going to say the voltage across C2 and C3 and C4 are equal to the voltage across 2, 3, 4? Think about that for a moment. Press pause and then come back. Well, what you should have known is that if these elements are in parallel, they're all holding hands, then the voltage across each one of those elements is going to be the same. So this is the answer to that question. The voltages will be the same. So now I go through and I say, well, I know the voltage on C2 and C3 and C4 are the same as the voltage across the equivalent capacitance, which we already calculated previously as 12.5 volts. And then we can just apply Hitler's equation to each one of those capacitors to find the charge on each one. So Q2 equals C2 V2. So there was the 10 for the C2 and the 12.5 there. And since they're all the same and they all have the same voltage, they all have the same charge as well. Well, we're going to end the show with one final example. This one's a little bit harder. All these capacitors are once again 10 microfarads, but I've numbered each one because as we go through and figure out the equivalent capacitance of each like mini little circuit in here, we want to keep track of what we're doing. So do you see anything that's either in simple series or simple parallel? Well, I'll tell you, a lot of people would say, what do they always say? Well, here's something that they say. C1 and C5 look like they're in parallel because these form parallel lines. But that's obviously not true, is it? Because they're not holding hands. You can't take one hand of this one and touch. See, you can't go to here because in order for this guy to touch hands with this guy, it has to go through the battery here on one side and it has to go through this capacitor on the other side, so it doesn't work. C1 and C5 are not in parallel. It's just the way they're drawn. I could have put C1 over here instead of here, and it wouldn't be, physically in parallel in the diagram. But that means nothing if they're in parallel in the diagram. If they're in parallel, they have to hold hands. And I don't see anything in this circuit that's in parallel. Because if I try to see, these two hold hands here, but they don't hold hands on this side because this there's somebody in the way. So C3 is not in parallel with C2, and I can't hold hands with C1 and C3 are holding hands on one side, but they're not holding hands on the other side. Are you getting this? All right. What you should have noticed, though, is C2 and C4 are in series, because if you were an ant walking through this circuit and you went through C2, you'd have to go through C4 to get out. You couldn't say the same thing about C2 and C3, because if you were an ant going through the circuit, you could go through this way and go through C3, or you could go this way and go through C2. So there's two different alternatives, so C3 and C2 are not in series, but C2 and C4 are in series. Okay, so then we can replace the series combination of C2 and C4 with a single capacitor. It's called C24, and its equivalent capacitance is found using the equation for the equivalent capacitance of series combinations of capacitors. So that's 1 over 1 over 10 plus 1 over 1 over 10, which gives us 5. So these two capacitors put together, they're both 10, give a capacitance of 5 microfarads. Then you look at the circuit again. We're not done. Do you see anything that's either in series or parallel? Think about it for a moment and then come back. What you should have noticed is that these two capacitors are in parallel because they're holding hands on either side. There's one side and here's the other side. So if they're holding hands on either side, they're in parallel. So I can replace the parallel combination here with a single capacitor I'm going to call C234. I could call it C324. It doesn't matter what order the numbers are in. And that's what I called it here, 324. So I find out the capacitance, the equivalent capacitance of two capacitors that are in parallel by just adding up the capacitors. So I had the 10 for the C3, and then our C24 was 5. Remember, that was the series combination of 2 and 4. So then I add those two together and I get 15 microfarads for C324. Then you ask yourself, once again, we haven't finished because we have to reduce our circuit to one element. So do you see, are these three capacitors in series or parallel with one another? What you should think of is if you were an ant going through one of these doors, you'd have to go through this door and this door. And there's no way to get out without going through all three doors. So then we can say that those three elements are in series. So I'm going to replace them. Sorry about that. I'm going to replace these three elements with an equivalent capacitance that I calculate using the equation for equivalent capacitance. I'm going to call it 1, 3, 2, 4, 5. Again, the order of the numbers isn't important, but I like to kind of keep them organized a little bit. So it's 1 over 1 over 10 plus 1 over 15 for the C324 plus 1 over 5 for 1 over 10 for the C5, which was just the 10 microfarads, and we end up with 3.75 for our overall capacitance. Okay, but we're not done because now we have to go back the other way. And the first step is to find the voltage and charge on our total equivalent capacitance. And to do that, we apply Hitler's equation. Q13245 is equal to C13245 times V13245. So that's 187.5 microcoulombs when you plug in the numbers. So now, then we're going to march backwards. Every step that we took initially to get the equivalent capacitance of the entire circuit, now we're going to go back the other way, and so we're going to go back from here to here. So will we say that the voltage on each one of these elements is the same, or will we say that the charge on each one of those elements is the same when we go backwards? Well, you should say that since they're in series, the charge has to be the same. So I write the charge, this total charge, is equal to Q13245 is equal to Q1 is equal to Q324 is equal to Q5. So then I made the charge on each one of those capacitors the same as my total charge. If they were all in parallel, I would have made the voltage on each one of them the same. Well, what we're going to do in our next step, we've got the charge on each capacitor, but we don't have the voltage. So we'll use Hitler's equation, Q equals CV, for each one of them, and then so V1 is Q1 over C1, V324 is Q324 over C324, and V5 is Q5 over C5. So now I've got all three voltages, and we can check to make sure that the sum of those voltages around that loop is equal to 50. And I'll let you do that on your own. So we're still not done because we still have this C324 to deal with, but we are done with C1 and C5 because we have the charge and voltage on each one of those elements. So now we have to go backwards from this C324 to this combination. Boy, we've got a lot of steps in here. So we have to go back to that combination. So will you say that the charge on each one of these is the same? Is the charge on C3 equal to the charge on C24? Or is the voltage on C3 equal to the voltage on C24? Think about it. What you should have said is it's the voltage, because since they're in parallel, they're holding hands so that they see the same voltage. So then I'm going to say V3 is equal to V3 is equal to V24, which is equal to the total voltage that we calculated over here. So there I've just drawn in those voltages to make it obvious for us. And then our next step, we know the capacitance and voltage of each one of those elements, but we don't know the charge on each one. So we apply Hitler's equation, Q equals CV for each element. Q24 equals C24 V24, Q3 equals C3 V3, and we get the charges on each one of those capacitors in that parallel network. And we're almost done. We now have this C24, and we have to go backwards to the those two elements that are in series. So are you going to say that the charge on each one of these elements is the same, or are you going to say the voltage on each one of them are the same? It's not voltage, it's charge. When they're in series, one plate is stealing from the other plate. Those internal plates steal from one another and make the charge all the same for a series combination of capacitors. So we say the charge Q is equal to the charge 4, which is equal to the charge which was 2,4, this one right here. And how are we going to find the voltage on each one of those elements? Well, I don't actually work this for you as we've done this so many times. You're just going to use Hitler's equation, Q equals CV, for each one of those elements. So I'll say Q2 equals C2 V2 and Q4 equals C4 V4. And then once you do that, you find the voltage on each one of those, and you'll be done, because now we have the voltage and charge on each element in this wonderful circuit. Well, what did we learn today? We found that capacitors in parallel are holding hands so they see the same voltage. Capacitors in series have to steal charge from each other, so they must all possess the same amount of charge. We use Hitler's equation, Q equals CV, to find the charge once we have the voltage on a capacitor. In order to work complex capacitor circuits, we reduce them to a combination of simple series and simple parallel capacitor networks. And we have to apply the rules for parallel and series capacitors to go backwards and ultimately find the charge and voltage on each capacitor in a complex network. I hope you've enjoyed the show.